Yeah, thanks very much for the invitation. It's a great pleasure to speak here today and to see so many experts here in my scientific home in Bremen. Very nice, so I'm looking forward to a very nice week with all of you. I'm going to talk about AI-empowered next-generation multiscale climate modeling for mitigation and adaptation. So this is work we are doing as part of the ESC Synergy Grant USMILE that we won that started in 2020, and I'm coordinating jointly with Pierre Chontin, Gustavo Kamsvals, and Markus Reichstein. I want to acknowledge my group members and also our collaborators. So my prediction is that AI will play an integrative and very powerful role in climate modeling, not just in coffee break. So what I want to argue for is that we need to use the full hierarchy of models. Clearly, very nice development, as we have just seen on the kilometer scale, high resolution, cloud resolving, climate modeling side. But what I would want to convince you here is that we really need an integrated approach where we use ML to enhance also coarser Earth system models, and this approach will in the end also benefit the kilometer scale models. We have machine learning downscaling to bring it back to output scales that are required by impact models, and so we can provide better information. So AI has played a huge role already in weather forecasting. I mean, when you look at the weather forecasting models, there isn't any model now that doesn't fully built on AI. And this was very rapid development. I can also say in climate modeling, people are starting to utilize machine learning more prominently. But for climate, it is very different. So for weather forecasting, it's a fully data-driven problem. To me, it was not a surprise that this works very well. But when it gets to climate, the problem is that we have all these Earth system feedbacks and processes, so it's much harder to learn this just from data. There is progress. I just was visited by Junhee Lee from South Korea, and this group is working on a similar data-driven AI approach for sub-seasonal to seasonal predictions. For longer climate, we are taking another approach, which is hybrid modeling, where we combine machine learning with the physics of the Earth system model. That's one approach we could take, but I will also show a few others during the talk. So let's get a step back where we stand with climate modeling. You know that climate models have been coordinated as part of the WCRP project, the Coupled Model Intercomparison Project. I chaired it from 2014 to 20. And really, the models have made huge progress over time and were further developed in terms of system processes, but also made very important contribution as research tools for Earth system model understanding. We used the models in the most recent IPCC AR6 report for providing important information on detection and attribution, and also on climate projections, as you can see in the video down here. Yeah, okay. So nevertheless, so I think it's fair to say that CMIP was really extremely important over the years. We have managed to provide coordinated input to the IPCC reports. This is handed over to policymakers and gives the basis for action to be taken in terms of climate actions. Well, just want to remind that the first time IPCC has already warned quite concretely about anthropogenic climate change was already in 1995 by Ben Santer. So we are 30 years behind after this statement, and still atmospheric CO2 concentrations continue to rise. Nevertheless, back to the models. So what's the problem with these models? So we have answered the question, yes, it is anthropogenic climate change that we are seeing, but now we need to be more regional in order to answer the questions we have to answer now, which is really, as climate change has set in, we need to work towards providing more accurate information on the regional scale for adaptation to climate change and for mitigation of climate change. And here is what the problems major drawback is they remain to have systematic errors, as you can see here, for example, in precipitation. And when you look at these errors, the patterns of these errors, they really don't change over time, over the CMAP phases. So we always have the double ITZZ and several other biases, which is really hindering accurate projections on the regional scale. And why is this? This is because these models have a rather coarse resolution of around 80 to 160 kilometers. And so we need to parameterize everything that is subgrid scale, like a cloud. Of course, a cloud process doesn't occur on a scale of 80 kilometers. It also doesn't occur on a scale of 10 kilometers, but we can resolve the processes better. So our approach is to combine hybrid a machine learning approach that learns these subgrid scale processes from high resolution simulation or observations or end observations, and then include them in the physical model. Here is our approach. I will show you some examples from our work. We've worked through a variety of different parameterizations. This is still in the research phase, but we are working towards implementation phase now, as I will show you in later on. So the first parameterization we targeted by one of my first PhDs, actually starting in 2020, was the cloud cover parameterization. That's very simple. You just have to learn one value per grid box. So the cloud cover parameterization is based on the Sundquist scheme in the ICANN model that is our host model here. And you can see in the figure that we have an underestimation in the lower troposphere and overestimation in the higher troposphere. So what we do is, we have just heard, we have really brilliant high-resolution simulations. That's great development. We take short high-resolution simulations and learn the subgrid scale processes from these high-resolution simulations. So we coarse grain them to the horizontal scale of the coarser Earth system models, let's say 80 kilometers. As input features, we take the potential features that might be impacting the target variable, in this case, cloud cover. And then we train the neural net offline. We first test the offline performance, and we can show that by learning from Narwhal and Cubic and Diamond, all great simulations, we can learn the cloud cover quite accurately. However, with this approach, as I said, this was just a feed-forward neural net. We had several issues in terms of generalization. For example, if we trained the neural net only on the Narwhal region, and then we wanted it to generalize to the global, it didn't work. And several others. So during the course of the project and several PhD students, we worked on further improving trust, interpretability, generalization, and acceleration. Here are just some examples. So one important study was that we worked on causally informed neural net, meaning that your neural net doesn't learn like the full spurious correlations. It really, each output learns just from the causal drivers, basically the parents. That was a very nice study that improved trust. We also worked on stochastic neural nets. I will show a quick example later. And we are also working on accelerating the model, for example, the radiation scheme, which is quite expensive, with a goal to provide it to the ICANN model so that we can run it on higher resolution. One very promising approach in terms of interpretability, I would say machine learning isn't a black box anymore. This is an outdated worry. We have explainable AI, we can understand what the neural net does, and we can also use explainable AI to actually understand the climate system better. But in terms of complexity, it's very complex, obviously. So what is to me a very promising approach, or another alternative, is data-driven equation discovery. So what you want to do is you want to learn the equation from data. So we did the same thing here, taking high-resolution data, and then what you see here is a comparison of the various cloud cover schemes. And yeah, so When you want to compare all these schemes, we put them in a Pareto frontier. So this is an error and complexity plane. Here is the mean squared error on the validation set, and here's the number of parameters. So here in the upper right, very good performance, very high parameters. What we want to go down here. We want to still have a good performance, but we don't want to have the huge neural net. So here is the study I just showed you from the feed-forward neural net. What we did then is we applied a sequential feature selection. Sorry. So that means that you take the various outputs, you do them one by one, and so you learn which one is most important, and you reduce the problem. So you can start with like 22 parameters, you do this, and then you end up with like 5 that are really very important, and then when you add the others, you see that your root mean square error isn't getting much better. And this way we reduced the system, and then we used a symbolic regression to find an equation, and that is we used PySAR. And we arrived at an equation that, in particular, I should say it has 3 terms, and in particular, the second term did learn marine stratocumulus clouds in this region much better. And we also included physical constraints into this equation. So I want to say that this is really a very promising way of using data-driven equation discovery for learning some of these processes. It's very novel, but novel and accurate and physically interpretable. But the problem is that when we put it online, so we still have the problems that we derive all these things offline and then we put them online. And then obviously, as we are changing the cloud cover or the convection, we need to retune. So next step, we developed a fast automatic tuning approach with machine learning, and I'm not talking in detail about this, but I still wanted to bring it up because I think it is truly also a possibility for kilometer scale model tuning. The basic idea is that we use a downhill simplex algorithm, and we run the simulation. So we take the metrics, like a variety of the typical metrics that we discussed early on with Marco Giuditta from MPI, and we run the simulation then just for a day, shrink the parameter space for months, shrink the parameter space, and then for a year, and it works quite nicely. Okay, so on the left-hand side, untuned ICNA, machine learning enhanced with a cloud cover. First thing, we looked at it, left side, my student, oh God, it's looking awful. Yeah, no surprise, it's looking awful because it's not tuned. So we tuned it, and then we had, with this approach, we could show that we have indeed a very nice reduction in the cloud cover bias, and we couldn't find any metric by evaluating the model simulation. It is an AMIP simulation. Sorry, I haven't said this so far. It's not a coupled simulation. Yes, we're backing our steps towards that. Okay, so we do fine here. We were quite happy. What you need to do, and that's really important, that's why benchmark is absolutely required, generalization. So you can't expect that your model, because it's not like physically based, in principle, if you have like a neural net, you need to look at what it does in the generalization. And we are working on defining more out of sample experiments. But here's a typical one, the plus 4K. And what we could show is that it does do reasonable things in this plus 4K simulation. Okay. So I just show one more example on the convection very briefly. We used a more complex unit, a vertical unit, to learn convection in a similar way. We used actually an ablated unit, and what you can see is that the model was able to improve precip extreme events. This is the ablated unit is the brown one, and the high resolution is the blue one. We had with this first study, we had issues with when we run it, it's just crashing, and it wasn't stable, and it's blurry. So we worked further, and some of you might know the ClimSim dataset, which is, I will get to this in a second, which is it's based on the E3SM. it's a benchmarking data set, and they had a Kaggle competition for the machine learning community, and the winner was one of the winner was a bidirectional long short-term memory architecture, which we then used, and we now have a 20-year stable icon simulation. I should say we are still not there. It's not that we would put this in the final icon machine learning enhanced version that we are developing for CMIP 7, but we are working hard on improving it. Overall, some promising, really promising results here from the various studies. Our target is to reduce the systematic errors in the models. In this case, at the moment, 80 kilometers, but we are also having similar studies to improve the kilometer scale version, which still has parameterizations. And we are learning like shallow clouds and turbulence with a similar approach. So here for the 80 kilometer simulation, we can show that we have improvements in extreme precipitation, we have improved cloud cover, as I was showing. We also can reduce the diurnal cycle of precipitation much better than in the original CMIP models. This is through a stochastic neural net approach. And with a causally informed neural network, we can show that if the double IDCZ bias is not in the original training data, we also don't have it. The problem remains with the online simulations. Let me get to the benchmarking. So as I was mentioning, you cannot absolutely expect physical consistency. You have to test physical consistency and generalization. So the ClimSim dataset is developed by NVIDIA, by Mike Pritchard's group. That's mainly for the machine learning community. You can plug in different networks and architectures, and we learn a lot from which architecture is doing well. Of course, one thing you might want to consider, you might not want to use the most complex ones, because then when you put it in and you run it, then you have such an increase in computing time, and then you can as well run high res, so that's not the goal. So it needs to be a balance. We also develop hybrid ESM bench together with Tom Beukler from UNIL, and here we just want to bridge between the communities. It's really important to bridge the communities because the machine learning community has very different approaches. So when we had this climate bench workshop just in San Diego, organized by Duncan Watson Paris, and very nice workshop. So the machine learners want a leaderboard. So metrics leaderboard win. So it's not as simple because obviously the climate is so complex. You can have a model that's good in the tropics. It can maybe not be good in modes of variability or something else. So we really have to ensure we are benchmarking across the trends the model simulates, the means, the variability, and the extremes. We are utilizing the ESMVAL tool. We are also working towards different grids with this, coupling to the kilometer scale, high resolution benchmarking activities, which are great and which are so important to get a hold on our biases that we have in the models. We really need to reduce them. Okay, so here is our outline, how we move forward. Our USMILE goal. USMILE focuses on land and atmosphere. So we, as I was showing you, have developed individual machine learning based parameterizations by the individual PhD students. Great work. Now it comes to the stage where we have to implement. So we're currently in the stage of implementing together with Max Planck Institute in Jena, with Alex Winkler. We are developing the ICANN machine learning enhanced, ICANN XPP machine learning enhanced version, which we want to contribute to CMIP 7 with hybrid atmosphere, land, and also offer this tuning approach that we will try. And ideally, we would like to run coupled. We all know it would not be very wise to promise it works. So we all know once we have it in the AMIP simulation, it's still a big step until we have it solid in the coupled with the ocean simulation. So I'm not claiming we are at, we are kind of reached this now, but I think we have very good indications that machine learning can help us if it's wisely used across the scales and Earth system modeling. Just for completeness, because we are talking tropical and coastal here, we are not doing this, but I would like to refer to our sister projects, M2 Lines and LEAP, coordinated by Laura Sana and Pierre Chantin. And they are working on a similar approach for the ocean. And let me go to this first. And also I would like to refer to another work that's quite common now, is developing emulators. So that is an example from Will Chapman from ENCA and the University of Colorado. He's developing the Chemulator, and the emulation can also be very useful. You can think about emulating a specific component if you are more interested in marine biogeochemistry or like the ocean in detail. You might want to emulate the atmosphere and run it like this. And this way we can really, or when you tune, when you don't know which parameter to use, you can make much more sensitivity studies if you use emulator, machine learning based emulators. So it's kind of a very flexible tool. Of course, challenges remain. I would say I've already talked about we need to avoid that machine learning is regarded as a black box and something magic. No, it's not magic. It's not even a black box. It's really very nice and understandable with explainable AI. We are working on causality to bring in physics, which is nice. What we also need to do is to work across sectors. So private industry is entering massively into the sector. So collaborations between academia and the private sector are ongoing and are very fruitful. So these are the challenges: generalization, uncertainty, quantification. Again, machine learning can take a big strike. And we have other huge really chances with machine learning. We can create larger ensembles with machine learning. We can accelerate the model, so we can work towards a higher resolution in whatever model we have, so we don't need to make this distinction. We can work towards hybrid models where we have systematically reduced errors, both in kilometer scale as well as in Earth system models, and on physical constraints, and then on emulators. Okay, so overall, I would like to bring things together with this slide. So what we envisage is a fully AI-empowered next-generation multi-scale climate modeling approach, where, of course, kilometer scale plays an important role. I showed you here mainly work how we improve how we improve Earth system models with machine learning. We can do the same with the kilometer scale models, and we are on it. For the subgrid scale processes, we're also working on improving constraining with Earth observations. We take the output, we do regional refinement down to, say, 10 kilometers if it's a coarser one, and machine learning based downscaling to get down even lower to derive impact models. And with this, we can hopefully provide a better climate information also on the regional scale. As I was mentioning, for the tropics and coastal areas, there are various things where you can utilize this approach, including the emulators, but maybe also like emulating the whole machine learning the marine biogeochemistry in one run. In another one, you might want to have it very detailed. So I argue for a flexible system as a research tool, and as we move on, this differentiation will anyway be resolved, as we will, of course, all want to run it as possible high resolution anyway. But there's also the note that there are quite complex processes out there. We have to work further on permafrost, on the carbon cycle, on various other, like integrating ice sheets, and covering Earth system processes and feedbacks is continued to be required. Okay, so I will kind of close with a few summary and outlooks and some maybe thoughts. So I would encourage this AI-empowered hybrid approach, and to me it's not either or. We really need to use a hierarchy of models because some of the research questions could be very detailed. For some, you might require a large ensemble, really huge ensemble. So machine learning comes in for sure, whether through hybrid models or through other approaches to, for example, assess the likelihood of low probability, high impact events. It provides significantly reduced systematic errors. I want to say the caveat, we are not yet there. We still have to work it fully through, but we have good indications. It works for both coarser ASMs and kilometer scale. The automatic tuning approach is also a big step forward. We have another one because the one I showed doesn't work for like all applications. This 1 day, 1 week, 1 month. So for land atmosphere, we're using another approach, but machine learning-based automatic tuning is really a promising way forward. And I would like to see seamless development of ICANN across scales rather than separating the lines of development. So another recommendation is really make ML an integral part of our system modeling strategy. Integrate in ICANN developments alongside our system processes, components, and increase in resolution. We have it for, I already said this, acceleration, regionalization, creation of large ensembles, etc. And maybe one last point as a call towards everyone who's doing machine learning enhancement. I also discussed this with people at the Climate Bench workshop. So of course we want to share expertise. So we have everything is anyway open source, and but we really need to make sure that other groups that enter the field now don't do what we did over the last 5 years. We don't have the time. We need we need better models soon. So we are fully open to collaborate. I would think we would maybe even have a workshop on ICANN ML enhancement so that we don't duplicate work. I mean, we don't have time for that. We can learn from each other. One important point, and that's really a limitation, what we currently do, we try to do our own kilometer scale simulations because the output is usually not, the output we require is usually not in the standard kilometer scale. Simulations, what I would like to see is that we get together, define the output in these simulations for the machine learning work. It doesn't have to be for the full simulation, but we share LAS, high resolution simulations, so we can fully utilize AI. Thank you.